This video we're going to look at hypothesis testing, and because we've had a lot of our chi-square distribution tests, I just wanted to take the opportunity to compare them and show what's the same and what's different between the three tests that we've had. So remember, we've had a goodness of fit test, we've had an independence test, and a homogeneity test. Okay, so let's look at our first thing, our goodness of fit test. So we're going to use the goodness of fit test to decide whether a population with an unknown distribution fits a known distribution. In this case, there will be a single qualitative survey question or a single outcome of an experiment from a single population. And that's important because with our other two chi-square tests, our independence and homogeneity, we have more than two populations. So we're comparing that using a contingency table. The goodness of fit test is typically used to see if a population is uniform, so all outcomes will occur with the same equal frequency, but we don't actually have to have that. We just have to have some kind of known distribution to compare it to. For the null and alternative hypotheses, our null will be the population fits the given distribution. So remember, on a fair die, that would be like the probability of rolling a 1 would be equal to the probability of rolling a 2, a 3, a 4, a 5, a 6, and then all would have the same distribution of 1 out of 6. If we're looking at something that has a known distribution that is not uniform, so that could be something like M&M colors are not uniformly distributed, so each color has a certain percentage that M&M and Mars Company decides to put into their bags. So it's still a known distribution, so we could still use this goodness of fit test because it would just be different colors, but it would only be one population. We're just looking at M&Ms. The alternative is trying to show that the population does not fit that given distribution. Moving on to our test for independence, we're going to use this test for independence to decide whether two variables or factors are independent or dependent. And usually it's in the wording of the problem. We want to show that they're related or not related. That would be another way to say independent or dependent. So independent means they're not related, and then dependent means that they would be related. In this case, we're going to have two qualitative survey questions or experiments and a contingency table. And really, you can have more than two. We saw an example of that, but that contingency table will arrange our information and our data so that we can find those observed and expected counts. Okay, so our null will be the two variables or factors are independent, whatever that may be to the problem, and the alternative would be that they are dependent. Moving on to our last test, we have the test for homogeneity, and this is where we want to see if two populations have the same distribution, but this time we're going to decide if two populations with unknown distributions have the same distribution as each other. So remember, with that goodness of fit test, we had some kind of known distribution to compare to. Here, the test for homogeneity, we don't know the distribution, but we just want to see if the two populations are the same. So we're looking at one single qualitative survey question, and we've got our null being that the two populations follow the same distribution, and the alternative, the two populations have different distributions. Let's review things that we will need for a chi-squared test, and I'll just itemize them by the type of test. So the first thing we'll need for all three tests are expected counts. For a goodness of fit test, our expected counts, because we do not have a contingency table, we can easily find that by calculating our n, our sample size, times the probability of that event occurring. So for each one of those, we could do that entry. The independence and homogeneity, because we're both using a contingency table for those, they are calculated the same way. For each entry, so row 1, column 1, we would do row total, column total, divided by table total. Second thing we'll need are observed counts for all three of these tests. Those will be given, so there's no work to be done there. The conditions for all of these are the expected counts are greater than or equal to 5. The test statistic is the same. The degrees of freedom are different, but our calculator takes care of that for us, so we're not going to be too concerned with that. We would really need to write down our degrees of freedom if we had a chart that we were using for our chi-squared, because they do have a table for it. But our calculator is a great resource, so we want to use that. For the p-value, we do have a little bit of difference here. So for the goodness of fit, we enter observed values in L1 and expected values or counts in L2. And depending on the model of your calculator, you can either use a goodness of fit test, or you can use up our list here. So use L, whatever list you're using, and sum that L3. So I just put this number here because it doesn't matter what list you use to sum. Usually I use L1, L2, and then I just use L3. For independence and homogeneity, those are the same. So that's where we use our matrices. Observed values go into matrix A, expected counts into matrix B, and then we use that chi-squared test from the stat menu. So remember, that's stat, test, and then that chi-squared test is way down at the bottom, so you just have to keep entering down, and then that menu will come up where it will have those matrices already in there, and then you just press enter. One last review. Our steps in hypothesis testing, no matter what test we're doing, and that is true of any test that we do. For our p-value method, we determine the null and alternative hypotheses, select a level of significance alpha, find the test statistic, usually done in your calculator, determine the p-value, again usually done in your calculator, make a decision based on your p-value and alpha, and then state that conclusion.